Hello, my name is Tumbajan and I'm going to take you through the semantic aware spatio-temporal data warehouse for micromobility, which is the case for MakFleet Bodaboda network at Makerere University campus. So I'm going to take you introduction using the keywords and have Bodaboda and basically this is like a primary micromobile mode on the campus, and there is a high frequency and erratic routing or safety risks from it. So in this project we have the spatial-temporal data, which is the GPS accelerometer streams, which are sampled every 5 seconds. Also we have the knowledge graphs, which are graph-based semantic warehouse or like nodes, and in these nodes we have the intersections between intersections, vehicles, drivers, and also edges. We have the routes, events, and relationships. Also AI models like STGNN, spatial-temporal graph neural network, which is a message passing across campus routes, topology plus LSTM across time, semantic awareness. We also have privacy by design, and we have the telemetry, which is the real-time collection and transmission of motorcycle operations data, like the speed, location, to the MakFleet system for safety monitoring analysis. Also we have the episteme trust and micromobility. So with the related works with this project, we have all those. I'll just sample out one. I have the first one, which is the UTL for this paper was written in 2018. The model that was used is STGCN. Results where it outputs LSTM on METRLA, and the architectural limitation it had, it's a static graph which cannot handle topology changes, and the context limitation it has, the city road sensors all like not having vehicle level IoTs, and the rest as below. So the problem statements, first, a domain application problem. These bodabodas on the campus operate with no phone monitoring. They're just still the monitoring is still not via the cloud, it's still local. Also reckless driving incidents near the pedestrian zones, university administration which lacks the real-time safety intelligence or monitoring and analysis. Also the demand surges between the rush hours, as well as no data infrastructure that exists to enforce campus traffic policies. So the computational problem that we observed, the operational safety plus the spatial-temporal optimization, weak supervision, where they have the IoT telemetry plus the OSM geospatial mapping, anomaly detection, which involves reckless driving, plus the demand forecasting, the multi-rate time series on the spatial graphs that involves almost like 212 nodes and 476 edges. Also continual learning across semester concept drifts, privacy preservations, edge to cloud streaming into the semantic knowledge graphs, and lastly the STGNN plus the rule-based symbolic neurosymbolic architecture. Then we have the research contributions or the outputs. The STG data warehouse basically involves the use of spatial-temporal knowledge graphs for campus micromobility. and around 826,260 semantic events. Contextual stop has a distinct or ontological label separating safety stops from reckless braking, hash breakings, and others, as well as the semantic data engineering pipeline, where we built a three-phase IoT pipeline. It involves the crystallographic provenance, HMM matching, achieving a 90.6% confidence, and thirdly, the semantic event enrichment, distinguishing 6 event types using the campus ontology. Also, among the outputs, the custom. Also, we have the custom STGNN with OOD protocol, where we developed a novel GCN conv plus LSTGMM architecture trained exclusively on the semester 1 data. This one is used to like the semester 1 data is used and also evaluated on semester 2. Therefore, the Eastern Campus zones, or like the Spatial OOD, therefore achieving a AUC which is close to 1, which is 0.9785. Also, the business dashboards, where we deployed the first semantic evidence generation platform for border safety, and different anomaly flags are triggered. Therefore, rendering why a driver was flagged, not just a risk score. Also, our methodology and system architecture, we basically 3 phases. We have the IoT ingestion and provenance, the semantic pipeline, and also knowledge graphs with the analytics as shown there. So with our data set and the EDAs, so the data set basically just simulated with our source was simulated over MakFleet OSM road network, which involved about 15 borders with IoT equipped, which are IoT equipped with IoT devices. So the record had about 826,260 telemetry ticks. Semester 1 involved about 496,559 records, and semester 2 about 329,701 records, and the sampling was about 5 seconds per vehicle, and all those, and each graph, the graph gave about 212 intersections and 176 road edges. Normally rate that was given out was 8.8% of all the records, and the peak hours, as I mentioned below, before, it was the peak hour that we used, it was 8 a.m. So as we see from the graphs, we have the trip volume by hour of day, which shows the peak hours of morning and evening around 8, and also around late afternoon or late early evening, and the anomaly rate by hour of day in percentage also describes it that way. So in the EDA's results, we have the event type descriptions, where we have the count, the event distribution. Here we have the different events against each count, and we see that the normal travel has the highest count, and among the other anomaly events, we have overspeeding, which is almost more higher than the rest, with a count of 63,222. And on the sovereignty score distribution, anomalies only, whereby you have the one that is dominant over the others, which is speeding, with a sovereignty score of almost 0.8, and a count about 60,000. As you saw below, it is 63,222. Then the driver risk profiles we have here, we can know which one gave a certain event or risk score, and you can see that antivirus here, it has the highest risk score, almost about 1, which is close to 100%. And when we cross that, or when you verse it, each risk profile against anomaly rate, you can see those in green are a bit, the anomaly rate is low, and the anomaly rate for these ones that go beyond over 0.6 in red, where we have NumTable, as we saw here, with almost close to 1, is in the red upwards. Then the speed distribution by semantic event type. We have the speed that is matched over versus the event, different events. We see that speeding is at a higher level, almost 40 kilometers per hour, and the hash breakings and rapid accelerations, which are also somehow high, 30 and above kilometers per hour. Then we have the event year counts for semester 1 versus semester 2, as well as the event mix in percentage. So for the event counts, we see that that of semester 1 is higher than that of semester 2, and the event mix are relatively close or same for both semesters, with each event, hash breaking and normal travel, rapid acceleration, and speeding. And lastly, we have the accelerometer X distribution by event type and map matching snap distance in meters. So you can see here the longitudinal acceleration in meters per second squared against density. We see that hash breaking takes a lot on this graph with the highest density, as well as the rapid acceleration with rapid acceleration at the end here, and in the middle we have the speeding, which is relatively high. And on the map matching snap distance, we see that what did I do? Okay, so we see that distance from the GPS point to matched map road edges in meters, the greater the distance, also the lower the count, and the median that was calculated was 4.3 meters. So the architecture and mathematical foundations are as below, where I had the candidate selection with the knowledge, that's where I have the tree query edge within 30 meters radius, emission probabilities, transition probability, antibody coding, and the output, which was the matched edge of U and matched edge V. Also the mathematical foundations as seen there. So just to continue from the other side, we had with the input of t equal to 4 graph snapshots of which were multiplied by the nodes, which were 212 with the 6 features. We have the spatial encoder, where we have the shared and which is shared snapshot. Also the temporal generator, which is aggregator, which is per node, and the output, which is linear. So the results that we obtained, the validation of semester 1, which were, well, we have the score which is close to 1, which is 0.9067, precision, which is 0.8293. Also recall, which is 1, and samples, which are 1728. The temporal OOD semester 2 samples were over 5,757, and around the Eastern campus obtained 5,719 samples. So we benchmarked the STG KG versus the star schema query performance, and on query 1 we obtained a median of less than 50, with traffic density control approximately 60, reckless drivers near zones less than 80, and causal chain traversal less than 100, semantic zone aggregation approximately 70, for all that for the ST KG median, and the star schema median as there. Then expressibility in SS. So the first query was partial, second yes, another partial, another no, and another yeah. Then why did we choose this model? Basically this one, it is inductive bias. The GCN inductive bias matches spatial graph geometry of campus networks. So also the LSTM captures temporal dependencies across 15 minutes windows. Also the rule-based component. We have the semantic enricher, which provides a symbolic interpretability. The scientific justification, or like comparing with other alternatives, random forest lacks spatial graph inductive bias, and also the SNN no relational structure, and the rest as there. So the deployment of a Docker, and also a fallback to rule-based score if a checkpoint is unavailable, and the deployment pipeline is as shown there. So with this demo, we can see it. The demonstration, it shows the business intelligence dashboards and all the AI insights that can be used by the administrators for better decisions.
Hello, my name is Numbachana, and I'm with.
So if I go forward, the technical limitations that we face are data that was simulated. We simulated a data set, and the limitation whereby no real border GPS data that was collected. Simulation uses OSM road topology with calibrated noise. A suggestion that we got was that we have to deploy the IoT devices on the actual border, or partner with KCCA or campus transport office for real telemetry, so that we can capture the real data. Also the model training, we trained the model for only 10 over 50 books due to the GPU constraints. And lastly, the architecture static campus graph, whereby we are limited on the same road network, which is fetched once and cached. So as I conclude, we successfully designed and implemented the knowledge graph for the border fleet management, semantic pipelines, which achieved over 90.6% matching confidence, and correctly enriched over all those telemetry records. And future developments, basically implementing and deploying the real IoT telemetry units and the real actual borders, implementing the online learning, and updating or incrementing the model on each semester without fully retraining to adapt to console drifting, the others. And lastly, publishing the MakFleet ontology as a linked open data set to contribute to the African Smart City Knowledge Commons. So we'd like to extend our acknowledgement to the supervisor, Department of Computer Science, the OpenSuite contributors where I obtained our dataset, and also the open source community. Thank you.